All right, so here is the solutions guide to practice exam 1. So let's get this thing going. So question number 1, I'm not actually going to go over it, but it is going to be on the exam. Is just a blank unit circle, and you fill it all in. So figure out what all the points are, include both radian measure and the x and y coordinate point. Uh, we'll have roughly 16 questions that are just simply find this thing in the unit circle on the exam. So yeah, here's a blank unit circle, fill it out. But I'm not going to do that because it seems like a lot of work for not a lot of utility. Instead, we'll move on to question 2. Notice that I scribbled something out on question 2 because this one was over-defined. It had too much information, and in fact, the information conflicted with itself, so I just deleted half of it. So we're going to use the fact that sine of theta is equal to 1/9 to find the exact value of cosine theta. Reduce any fractions if necessary. So if I know that sine of theta is 1/9, and I want to find cosine of theta, let's also give the added information that tangent of theta is positive. So tangent theta is positive and sine of theta is 1/9. Because we'll end up needing to take a square root, and we'll need to know if we want positive or negative. So use only trigonometric identities to find the exact value of cosine theta. So if I want to relate sine and cosine together, I have that Pythagorean identity. It says that sine squared plus cosine squared is equal to 1. So we're going to use that here. Sine squared plus cosine squared equals 1, meaning that cosine squared of theta is equal to 1 minus sine squared of theta, which is going to be 1 minus 1 over 81. And I'm going to change that 1 to be 81 over 81. Just that I have a common denominator, meaning that I get 80 over 81. So cosine theta should be the square root of that. And if we look back up at that given information, sine of theta is positive and tangent of theta is positive, must mean that we're in quadrant 1. So we'll take the positive of the plus or minus choice, and we'll simplify that square root as much as we can. 80 is 4 times 10, or 8 times 10, which is 16 times 5. 16 is a square number, so that can come out. This will be 4 square root of 5 divided by 9. All right, coming over to the chat, why couldn't we use the cofunction identity on this problem? And the reason that we're not going to want to use cofunction here is that we don't have any complementary angles happening. All we have is just that sine of theta is equal to 1/9. So while it is true that sine of theta is equal to cosine of pi over 2 minus theta, it wouldn't help us here because, again, we don't have any complementary angles going on. So instead of a cofunction identity, because again, no complementary angles, we'll instead use a Pythagorean identity. Okay, number 3. Using the unit circle and coterminal angles, find the exact value of each of the following. So what do we want here? So it looks like we're going to want to find some coterminal angles in each of these cases. So negative 4 pi over 3. I'm going to want to add 2 pi to negative 4 pi over 3 in order to come up with a coterminal angle. 2 pi is equal to 6 pi over 3, just to give ourselves a common denominator. So that's 2 pi over 3. So the cotangent of negative 4 pi over 3 should be the same thing as 1 over the tangent of 2 pi over 3. Right, so we'll replace our negative angle with a coterminal one that is familiar from the unit circle. We'll also use the fact that cotangent is equal to the reciprocal of tangent to ultimately come together and say that this is 1 over negative square root 3, which would be negative root 3 over 3. So if we talk about what this will look like on the exam, which is all multiple choice, because, well, you wouldn't be wrong if you stopped at negative 1 over square root 3. That won't be an option in the multiple choice. So 1 over square root 3 won't show up in the multiple choice section. And instead, the rationalized answer of negative root 3 over 3 is what would show up in that multiple choice bank. So make sure that you can rationalize far enough to get to whatever answer I might have in the multiple choice bank. So again, that 6 pi over 3 is just equal to 2 pi. So I'm adding 6 pi over 3 because I needed to add 2 pi to find a coterminal angle. We'll see that we're going to do something very similar in the next problem, where I have 17 pi over 6 and I want to find a coterminal angle, but this time I'm going to subtract 2 pi instead of adding 2 pi because I have an angle that's too large. So in the case of a pi over 6 angle, 2 pi is the same thing as 12 pi over 6. I just did that so that I could get a common denominator and actually subtract these two things to end up with 5 pi over 6. Now that I have a coterminal angle that's familiar from the unit circle, this just becomes a unit circle problem. So the sine of 17 pi over 6 has the exact same value as the sine of 5 pi over 6 because those are coterminal angles. And the sine of 5 pi over 6 is a value we know from the unit circle. It is 1/2. Then we'll move on to the cosecant of 7 pi over 4. This will be 1 over sine of 7 pi over 4, which is 1 over negative root 2 over 2, and that will simplify to negative square root of 2. After we flip our fraction and rationalize, it comes out to negative root 2 over 2. So a quick demo of how that happens. So 1 over negative 2 over root 2. We'll start by taking a reciprocal, which makes this 2 over root 2. I'd like to rationalize this mess, or rationalize the denominator rather. So I'm going to multiply top and bottom by the square root of 2. Doing so gives me 2 root 2, over square root of 2 times the square root of 2 comes out to just 2. Don't forget your negative sign. And at this stage, 2 over 2 reduces to give us just negative square root 2. Let's change that back to black. All right, problem 4. Given the following triangle, state the requested identity and then find the exact value of said identity. So stage 1, I have the secant of 90 degrees minus alpha. This should be equal to the cosecant of alpha. Right? It's just a cofunction identity, and it's just a straightforward directly from the worksheet. Which means that if we want to get the cosecant of alpha, it's equal to hypotenuse over opposite, since it's the reciprocal of sine. So we need to know what our opposite side is. Unfortunately, we're missing that right now. So we'll need to use the Pythagorean theorem in order to solve for that side B. So if we run through that work real quick, I need the square root of 57 squared plus b squared is equal to 11 squared, meaning that b squared is 121 minus 57, which will simplify to 64, meaning that b is 8, the square root of 64. Because this is just a triangle, it's not put into the coordinate plane. So just simply a triangle, all sides are positive. Because we're not looking at it as like some points somewhere in the coordinate plane. It's just a triangle. So we don't need to worry about the plus or minus on that square root of 64. Although I don't think I'd mark you down if you put negative 8. So the cosecant then was hypotenuse over opposite. So this thing becomes 11 over 8. All right. Then we've got the multiple choice section. Well, I suppose the actual exam will be all multiple choice, but on this written part, there's a multiple choice part that goes with it. So all of the questions on the exam will have a fairly similar format to these next few. Hey, buddy, you're awake. Let's see if you can see Cooper in the background. He kind of blends into the light right there. Okay, so given that cotangent is negative and secant is positive, find the terminal side of an angle theta. So what do we know? If we throw up some coordinate axes, cotangent being negative means it must be either in quadrant 2 or 4. So those are the two places where cotangent is negative, because it has the same sign as tangent. Then if secant is positive, that's the same thing as cosine being positive. And cosine and secant are positive in quadrants 1 and 4. Let's do boxes. So the spot where these two things overlap is quadrant 4. So our angle theta must be in quadrant 4. All right, then an angle in standard position that measures -8 radians is in which of the following quadrants? So first thing I'll do is find a coterminal angle that's positive. I think that'll be the easiest way to do this thing. So I'll take -8 and I'll add 2 times 2 pi. Since 2 pi is about 6.28, so if I only added it once, I'd still have a negative angle. Adding it twice, though, I'll end up with some positive number. 6.28 times 2 becomes 12.56, and 12.56 minus 8 would be 4.56. So -8 is in the same position as 4.56 radians. And if we throw those decimal approximations for the coordinate planes up above, we have 0 radians is right here. 3.14 radians would be pi. Again, we said 6.28 is 2 pi radians. Pi over 2 radians is about 1.57. 3 pi over 2 radians is about 4.71. So our angle of 4.56 radians would be about right here. Somewhere in between 3.14 and 4.71. Meaning that we are in quadrant 3. So in order to convert all of these radians into decimals, you can just multiply whatever times pi in your calculator. So 1/2 times pi is 1.57 approximately. 1.5 or 3/2 times pi is about 4.71. 2 times pi is about 2.68. And pi itself is about 3.14. Right, problem 7. We've got two coterminal angles for -7 pi over 15 are the following. So what we'll do is we'll take our -7 pi over 15 and I'll do a couple of things here. The first time I'll add 2 pi, which 2 pi is the same as 30 pi over 15 to give ourselves that common denominator. And then we'll also subtract 2 pi. So we'll both add and subtract it and get a couple of coterminal angles. Adding 2 pi, I end up with 23 pi over 15. Subtracting 2 pi, I get -37 pi over 15, which must be option E. Problem 8 wants us to find the reference angle for 37 pi over 30. So step one is figuring out which quadrant 37 pi over 30 is in. And what I would do is just look at the 37 over 30 part. And you can get a decimal approximation for this if you'd like. But we should find that 37 over 30 is definitely bigger than 1, because 37 is bigger than 30. But it's not quite as big as 1.5, since 1.5 would be equal to 45 over 30. So this thing is less than 1.5, or rather, it's less than 3/2. So because 37 over 30 is between 1 and 3 over 2, that means that 37 pi over 30 is in between pi and 3 pi over 2. So this angle must be in quadrant 3. And in quadrant 3, we know that the reference angle is equal to our angle minus pi. Make sure this slides all the way over so we're not running into that sidebar. Our angle was 37 pi over 30. Pi is 30 pi over 30, meaning our reference angle is 7 pi over 30. Which must be option A. 7 pi over 30. Looks like we don't have a problem 9. All right, so on to the free response. So problem 10, given the radius of the Earth is approximately 3,960 miles, find the distance between Dallas, Texas and Omaha, is that Newfoundland? One of the Canadian province, or no, Omaha, Nebraska. Why did I think any was a Canadian province? Glad I recorded myself doing that. So yeah, cool. Find the distance between Dallas and Omaha. Fortunately, you don't need to know that Omaha is in Nebraska in order to effectively solve this problem. So let's do this. Put what's roughly a circle up here. Hey, now don't give me that. Okay, fine. Fine. Be that way. Draw a slightly better circle. It's going to be the Earth, so we might as well make it blue because, you know, the Earth is mostly water. That's unhelpful. Don't forget to silence your phones during class. I haven't had to say that in a long time. Okay. Let's come over here and draw the equator because I'm going to want the equator. Hey, come on. 0 degrees. Perfect. So if we put the equator on our Earth over here, and there it is. Okay. And then we have two cities, one that's at a latitude of 32 degrees and one that's at a latitude of 41 degrees, you know, roughly speaking. And I'm going to have to exaggerate this a bit so we know what it looks like. One city is about here. The other city is about there. Ignore the fact that these aren't going to be quite drawn to scale. So we've got these two cities where we happen to know this angle and this angle. So cool. We got our city sketched out over here. Thing we're looking at is the arc length between our two cities. Again, those cities being Dallas and Omaha. They're not really that far apart on the earth, but I exaggerated the drawing so we could see what we're doing. We need to do a couple of things. First, we want to know what our angle theta is. Let's just quit rambling and do it. So theta that's going to be of interest to us in this problem will be the difference between the two angles. So look at 41. 41 has a 1 before the decimal point. Minus 32.79. And we'll get a number over here. This is 8.47. That's 8.47 degrees. Right? Yeah, it looks like it's 8.47. So now that we have our angle in degrees, we want to find the actual arc length, S. And S is equal to R theta, where R is 3,960. Theta is 8.47 degrees times a conversion factor of pi over 180. Because it's very important that theta be in radians. Otherwise, this whole formula doesn't work if I keep theta in degrees. But we can take all that to the bank. And by the bank, I mean a calculator. 3960 times 8.47 times pi divided by 180. And I got 585.40. And that'll be in miles. Cool. Seems like that worked. Go team. Right, moving right along. Problem 11, medical alert helicopter is flying at 734 feet. Helicopter emergency crew sees an ambulance at an angle of depression of 62 degrees. Find the distance of the ambulance from a point on the ground directly below the helicopter. So come over here and sketch ourselves a drawing. Or sketch ourselves a diagram rather. Hey. Don't be like that. Come on. There it is. Okay. Actually, come on. Man, okay. There it is. Draw ourselves a helicopter. Yeah. Can draw better. Yeah, there we go. That looks like a helicopter. Let's move it down just a little bit so it's right at the top of that line I drew. Yeah, helicopter. Okay. And then it spies that ambulance at an angle of depression of 62 degrees. So we'll measure ourselves a 62. Oh man, this is going to be pretty sharp. Cool. There we go. Got ourselves a 62-degree angle. Next thing we should do is draw that horizontal line up at the top where our helicopter is. Come on, there we go. Settle at 0 degrees. And since we know we had an angle of depression, that means that this exterior angle right here should be 62 degrees. Down below, we know we've got our ambulance is at that point. We have the height in the air that this helicopter is flying at. It's 734 feet. And finally, we know that angles of elevation and angles of depression should measure the same number, even if they are located in different places. So we've got this 62-degree angle down here. That's the angle of elevation, and it's the same as the angle of depression labeled above. Cool. So now that we have a beautifully drawn diagram, we've got to get our we've got to actually solve the problem. The thing that we're looking for is the distance down here. I'll just call it X. The distance from the ambulance to a point on the ground that's directly below the helicopter. So looking at our triangle that shows up in this diagram, I have a 62-degree angle. I know the opposite side is 734, and I'm looking for the adjacent side. So if I want to relate opposite and adjacent together, that means I need tangent. So tangent of 62 degrees is equal to 734 over x. Solving this thing for x means that I need 734 divided by the tangent of 62 degrees. And we'll take that to a calculator. 734 over tangent. Nope. 62 degrees. 390.27. And this time we're measured in feet. Once again, I'm using tangent this time because I know I'm looking to relate opposite and adjacent together. So let's take this diagram and move it up just a little bit. There we go. Now that X isn't bleeding into the next problem. Might make it a little easier to see when we come back. Okay, problem 12. We have the point -1/5, comma 4/5, and it's on the terminal side of an angle in standard position. Step 1 is deciding if this point is on the unit circle or not, and then after that, find the exact value of secant theta. So in order to be on the unit circle, we have to satisfy the equation x squared plus y squared equals 1. Since that is the equation of the unit circle, meaning that if we want to see if this point is on the unit circle, we should just square both coordinates, add them together, and see if we get 1. If we do, great, yes. If we don't, bad, no. Don't know why I assigned great and bad to yes and no, but I did. So we're just going to have to live with that now. Let's just keep moving forward. We're going to take 1/5 and square it. And then we're going to take 4/5 and square it. And see what comes out the other side. Notice I got rid of the negative because, well, if I'm squaring -1/5, the negative will get squared as well. So it's going to come out positive no matter what. This is 1/25. Blah. 1/25 plus 16/25, which is 17/25. And last I checked, that's not equal to 1. Since 1 would be 25/25, and 17 and 25 are not the same number, so it's not equal to 1. Meaning that point is not on the unit circle. Which means if we want to find the exact value of secant theta, we will unfortunately not be able to use just the reciprocal of -1/5 because we're not on the unit circle. So instead, we'll need to sketch a triangle. We have a negative x value and a positive y value, so we're in the second quadrant. Haha. Look at that beautiful diagram. Put a coordinate point down there. Theta is this angle. We know we have an x value of -1/5. We have a y value of 4/5. And we'll have a hypotenuse of, well, we did all the work up above to add x squared plus y squared to get c squared. So c squared must be 17/25. Hey. Again, that's because of that work up there. So c must be square root 17/5. Right, all that together, secant of theta, hypotenuse over adjacent, which is root 17/5 divided by -1/5, which is just negative root 17. All right. Then on to what I think is the last page. Well, the last page that's loaded so far. Question 13. Draw a reference triangle and label some stuff and then solve a few things. So what have we got? Secant of theta is equal to -37/35, and sine of theta is negative. So if both secant and sine are negative, we must be in quadrant 3. Let's try that one more time. 1, 2, 3. Quadrant 3. So we'll turn this into a triangle. So the coordinate axes up here. Put our sides on said triangle. Secant is -37/35. So 37 is the hypotenuse. 35 is the adjacent side. I'm going to put the negative on the adjacent side because the negative never goes on the hypotenuse. And I've got a missing side, y. So throw some work together over here. 35 squared, ooh boy, turning to shape off. 35 squared plus y squared is equal to 37 squared, meaning that y squared is equal to 144. So y is plus or minus 12. And because we're in the the third quadrant, I'm going to need to take the negative value here. So y should be negative 12. So yeah, our adjacent side is negative, our opposite side is negative, but the hypotenuse is positive. And the hypotenuse is always going to be positive regardless of which quadrant we're in. We'll only look at our two legs, being the opposite and adjacent sides, being positive or negative. Mm-hmm. All right, so we're going to use all of that information along with a couple of identities to solve for a few other values from this triangle. So we already know what secant is. Now we want to find the cosine of negative theta. And cosine is an even function. So cosine of negative theta is the same as just cosine theta, which from either from our reference triangle or from secant being negative 37 over 35, we get that cosine is negative 35 over 37. Our next part, we want the cosine of pi over 2 minus theta, which we know is sine theta, because that's a cofunction identity, and the cofunction of cosine is sine. And from that triangle above, sine theta is negative 12 over 37. And finally, it wants tangent squared, which from the triangle above, we know that tangent, which is opposite over adjacent, is negative 12 over negative 35. Then we can square that thing to get 144 divided by 35 squared. Which is 1,225. Oh yeah, and then everyone's favorite problem. So use trigonometric identities to solve the following thing, filling in everything that we can. So if we're going to solve a trig identity like this one, what is it that we got to do? So when I'm approaching a problem like the one that we've got before us, where we have to solve a bunch of trig identities together, the first thing I want to do is make sure that every trig function is using the same angle. So at the moment, I've got both 40 degrees and 50 degrees in floating around in different trig functions. And I'd like to have just one angle across the board. And it helps to notice that 40 degrees and 50 degrees are complements of each other, namely that 40 plus 50 is equal to 90 degrees, meaning that I'll be able to use some cofunction identities. So I can change either all of my 40-degree angles into 50-degree angles with a cofunction, or the reverse, which is probably what I'll do, is change all the 50-degree angles back to 40 degrees, again, using a cofunction. Also, I'd like to get rid of any negative angles that I have, and we'll use the even and odd identities to solve those. So I'm going to start by getting rid of negative angles. So here we go. 8 plus 3 times negative cotangent of 40 degrees minus 2 times cosecant squared of 40 degrees minus tangent squared of 50 degrees minus 3 times, looks like I'll need to slide this over to the left a little bit, negative sine of 50 degrees divided by the sine of 40 degrees. So looking at that first step, I've just used even and odd identities in those two places highlighted in blue. Cotangent is an odd function, so the negative gets factored out. Sine is also an odd function, so that negative comes out of the inside, and everything else I've left alone, at least for the first step. So all I want to do is just start solving these pieces. So now that I have all of my angles changed to a positive angle, I'll need to convert any angles that I want to get all of my angles to be the same angle. I have 5 trig functions. 3 of them have a 40-degree angle. 2 of them have a 50-degree angle. So I'm going to change all of my 50-degree angles into 40-degree angles. That'll be step number 2. So this will end up becoming 8 minus 3 cotangent 40 degrees minus 2 times cosecant squared 40 degrees minus cotangent squared of 40 degrees plus 3 times that next line. And looks like my handwriting is creeping up a little bit, so I'll give myself a bit more space. That numerator will become cosine of 40 degrees. I'll leave the denominator alone. And we end up with this. So notice in that second step, I'm only changing 2 pieces. I'm just going to change my 50-degree angles into 40-degree angles, again, using a cofunction identity. Okay. Now that we're here, we can start using some other trig identities. Everything else should start falling into place after I get all of my angles changed over to all being the same angle everywhere. So this will be 8 minus 3 cotangent of 40 degrees minus 2 times cosecant squared minus cotangent squared. That's one of our Pythagorean identities. It's equal to 1. put a 1 right here, plus 3 times cosine over sine is also an identity. It's cotangent. Now that we're here, we've got -3 cotangent 40 degrees plus 3 cotangent 40 degrees. Those two pieces add to 0. So I'm just left with 8 minus 2, which is 6. Maybe slide that over to the right a little bit.